Ciao, I'm Marco Magnaterra, and as part of the CRC, I investigate materials with exotic magnetic properties, in particular materials in which the electrons, carrying the magnetic moment, are delocalized over multiple sites, like in a dimer, a trimer, or tetramer. And I do this using resonant inelastic X-ray scattering. In practice, we go to a synchrotron, like the European one in Grenoble, and we bring our sample to the lab, and we shine X-rays with a very well-defined energy onto the sample, and we observe in which direction the X-rays are emitted and which energies are contained in the scatter beam. In particular, we are interested in the processes in which the X-ray hits our sample, the electrons in the sample, and they transfer part of energy and momentum to the electrons. So the X-rays will come out with a lower energy and with a different direction. We call this process inelastic X-ray scattering. We quantify this process by counting the number of X-rays that lost a certain amount of energy. So we draw what we call a spectrum. But the peculiarity of our technique is in the word resonant. Resonant means that the energy of the incoming X-ray is in resonance with the excitation of an electron from a very deep state, very well bounded to the nucleus, into the valence shell. So the valence shell is made of many quantized states for the electron, and these are the states we want to learn about. So in the RIXS process, one electron is pushed up in the valence shell, and one electron falls down, and when it falls down, an X-ray will be emitted, but the energy of the X-ray that is re-emitted will depend on which final state we ended up on. So we can have different energies of the outgoing X-ray, and what we measure in a spectrum would be free peaks in this case, and these peaks tells us directly information about which states the electrons can occupy in the valence shell. Now let's see an experiment done on this material here, and in this material there are two iridium dimers which are very close, and they are so close that the electrons are delocalized over the two sides. They form some kind of molecular orbital. Well, this is how a spectrum looks like. You can see three peaks, A, B and C, but what is most unusual and interesting is the behavior of the intensity of these peaks as a function of the exchange momentum, as a function of the scattering geometry. In fact, we could see a periodic sinusoidal modulation with maxima and minima. Why is that? What is that? So, in this case, since the electrons are delocalized over the dimer, you cannot tell with which one of the two sides your incoming X-ray is resonating with. So in other words, after the scattering, you cannot tell whether the X-ray resonated with one side or the other side, because they are undistinguishable. So what happens in quantum mechanics is that you have a superposition of the X-ray scattering on one side and on the other side. And this superposition can give rise to an interference. So you can have maxima and minima depending on the geometry. This is reminiscent of what was observed in the Young's double slit experiment, where when you shine a photon on two slits, well, the photon will go through the left slit and the right slit at the same time, giving rise to an interference which results in maxima and minima of intensity at a certain angle. So, now, if you do RIXS on these clusters and you see an interference pattern, well, this proves that the electrons are delocalized over these clusters. This tool was developed within the CRC, and this is what I'm using during my research to investigate more complex materials like trimers or tetramers.